I'm Doug Fernan. This is my take on music recording. Recording music is a technological endeavor. Technology is the root of everything we do, and everything a musician does too, for that matter. All musical instruments utilize technology to make them work. A piano, for example, is a marvel of mechanical engineering, which evolved over the centuries to become the versatile instrument we have today. The mechanism of a piano is complex. If you have an opportunity to look at the way striking a key results in a note, you will see how complicated it is. The hammer has to strike the strings in a way that it does not bounce and hit multiple times. Dampers have to mute the strings as soon as the key is released, and the pedals modify the behavior for various effects. We can see how a piano works because it's entirely mechanical. That's true for all instruments except those that rely only on electronics. And all the amplifying, processing, and recording equipment we use in the studio relies on basic electronic principles to make them work. Those principles are not intuitively obvious, but they are not very complicated. Do you need to understand how those devices work in order to record? No, you don't. Just like you don't have to be a musician or be able to read music in order to record. You don't need to know how your car works in order to drive it, or really have any understanding at all of our technological world to be able to function. But it's been my observation over the years that engineers that have at least some musical background are often better at recording than those that lack that foundation. Would understanding how your car works, or how your piano works, or how your electronic gear works be of any benefit? I think it would, and I think anyone in any profession needs to have more than a superficial understanding of their job in order to be really good at it. You don't have to have a degree in electrical engineering. I don't, but I have a need to understand how things work in any endeavor I might pursue. I'm not an expert at any of those things, but I have a moderate understanding of many things, and that helps me to do a better job. For example, I learned about the intricacies of piano action by observation and by asking piano techs to explain things to me. I study the history of keyboard instruments and how each new generation of them advanced the art. Each improvement in instrument technology changed the music that was composed and performed. The piano solved many problems of the preceding instruments. For example, the harpsichord has only one volume. It is not intrinsically capable of dynamics. The piano was originally called the pianoforte, the musical terms for soft and loud, to highlight its new dynamic capability. When I learned these things about the piano, it changed the way I placed microphones. It changed the way I recorded the piano in many ways, and I was much more pleased with the sound I was getting. It helped me to do a better job. Multiply that basic understanding of many instruments and learning basic music theory, and I think I became better at recording and producing. I am not an expert at any of those things, but I am curious and want to learn, and I want every advantage I can get to make better recordings. In my case, I was fascinated by science from a young age. Learning about electricity and electronics was important to me, although I had no reason to do so when I was 7. But as I grew up, that knowledge became increasingly valuable. So in this first episode in a series about basic electronics, I want to tell you about some fundamental principles that may help you to become better at your job. My explanations are going to be super simple, and because they are simple, they are also incomplete. Someone with an electrical engineering degree might have a fit at the way I explain things, but I want to provide you with insight, not deep knowledge. Just know that there are many layers of deeper theory behind what I am saying. Let's start with the basic concept of electricity, the circuit. The word comes from the same root as circle, and that helps explain the concept. A circuit has to be a complete path. The basic atomic particle in electricity is the electron. A flow of electrons is the principle behind all of electricity. Sometimes it is useful to think of electrons as water molecules, but the analogy is incomplete. Water can flow through a pipe and spill onto the ground, and as long as there is a supply of water, it can keep going. Water does not need a direct path back to its source, although on a large time scale it does. That analogy doesn't work with electricity because the electrons must always have a path back to their source. It has to be a circle, a circuit. The source of most of the electricity in our daily lives is an electrical generating plant. There, mechanical energy, or solar energy, is converted into moving electrons that are conveyed to your home or business through wires. Easy to see how that would work. It is like the water pipes that bring water to your home. But the water supply is not a circuit. Somehow those electrons have to return to the power plant to complete the circuit. Otherwise, the electrons would never move, and it is the movement of electrons that does the work we need. This is an imperfect analogy because each individual electron does not make its way back to the generator, but the concept works for our purposes. The same principle applies to every electrical and electronic circuit. Electrons have to return to the source to make it work. That's why electrical outlets always have at least 2 pins. That's why an audio cable has to have at least 2 pins in the connector. Just a flow of electrons is not useful. Somehow we have to extract some energy in order to make something happen. That could be providing light, generating heat, or making something move with a motor. That's the way our modern civilization works, at least in the majority of applications. Moving electrons provide the power to run almost everything. Electrons flow through materials that easily transport electricity. Those things, mostly metals, are called conductors. The most common conductor is copper. It is not the best conductor. Silver is the best, but silver is too expensive to use for most applications. Copper is second best and usually good enough. Your mic cables, power cables, and most internal circuitry uses copper wires. The third best conductor is gold, obviously much too expensive for everyday use as a conductor, but it has a unique property. Gold does not oxidize. Unlike almost everything else, it does not combine with oxygen in the air or in water to form a coating on a metal, and that coating is not a good conductor of electricity. In contexts where we have to avoid anything that would diminish the conductivity, gold is often used. Some examples are connectors, and in relays, a device we will cover later. Next best is aluminum. Not the best for carrying electricity, but aluminum is much lighter in weight than copper, so it is used for virtually all the wires that carry electrical power from a generating plant to your house. Lighter weight makes long spans of wire possible between power poles or tall transmission towers. To some degree, every substance is capable of carrying electrical energy. We classify things like silver, gold, copper, and aluminum as conductors. Things that are poor at transporting electrons are called insulators. Things that are good insulators are used to keep electrons from escaping the conductors. A typical insulator is made from plastic in some form. That is the coating on a wire. Without an insulating layer around the conductors, not only would electricity not be confined to its circuit, but it can also create a hazardous situation. If the electrons find a path back to the source before we want them to, that is called a short circuit. We have bypassed the intended destination for the electrons by providing them with an alternate, shorter path. A short circuit is never a good thing. Unconstrained electricity can cause major trouble in the form of heat that might start a fire or lethal danger to living things. Insulators are as important as conductors when it comes to electricity. The majority of substances in our world are neither good conductors nor good insulators. Surprisingly, those in-between elements also have usefulness to us. More on that coming up. Despite being good conductors, nothing is completely without loss of energy when electrons flow. And here is an important thing to realize. All those wasted electrons generate heat. In fact, all the electricity used in the world ultimately ends up as heat. The reason for the heat may be desirable, such as electrical heating elements to warm our houses or cook our food. But usually it is just wasted. Good design minimizes that lost energy by minimizing unwanted heat. A certain percentage of the electricity is always going to get turned into unwanted heat because no conductor is perfect. And that property of an imperfect conductor is called resistance. As you might guess, resistance is often undesirable. We want the electrons to work efficiently, not get wasted. But resistance is also a fundamental property that is necessary in many circuits, and the electronic components we purposely use for that application are called resistors. Why would you purposely want resistance? Well, let's take a simple application, a fader or a pot. If we want to control the level of an audio signal, we can use a resistor to reduce that audio level. Sure, it is throwing away some of the power, but in typical audio devices, the amount of energy lost is not that great. The loss is acceptable in order to adjust the level as needed. A pot or fader is an adjustable resistor. You can vary the amount of resistance as needed to control the audio level. Resistors can also be designed to provide a defined amount of resistance. Those are called fixed resistors, and they are a vital part of most electronic circuits. Fixed resistors use a material that purposely has resistance. The earliest resistors used carbon as the resistive element. Most modern resistors use a thin layer of metal, which has a known resistance. Resistors need to have a stable resistance. If they don't, our circuits may not work as designed. And like anything with resistance, some of the electrical energy in a resistor will be converted to heat. In addition to the amount of resistance, an important specification of a resistor is how much power it can safely handle. Before we continue, it is helpful to be able to quantify the various things we have talked about. We can measure the flow of electrons and the resistance to flow using precisely defined units. All of them are named after scientists who figured out how to measure them and how they interacted. Almost all these units were defined and well understood back in the 19th century. For example, the magnitude of electricity is measured in volts. Voltages in our everyday experience can range from very low, perhaps 1 volt or so, from a battery, to many volts. Most solid-state electronics need voltages from a few volts to tens of volts. Electrical outlets provide between 100, and 240 volts, depending on the application and what country you live in. Industrial processes may require many hundreds of volts, and for reasons I will explain later, the electricity from a power plant is most efficiently transported at much higher voltages, up to hundreds of thousands of volts. A lightning bolt is a form of natural electricity. It is unconstrained and is measured in millions of volts. Voltage by itself does not do any work until we extract energy from it to do what we want. That magnitude of the flow is called current, which defines the quantity of electrons flowing over a given time period. More current means more energy is being used to do something useful. Current is measured in amperes, which is usually shortened to amps. The resistance to the flow of electrons is measured in ohms. Another everyday unit of measurement is the watt. To determine how much power is consumed, simply multiply the volts times the amps to calculate watts. Typical wattages might be a tiny fraction of a watt in an LED flashlight, to tens of watts for most control room equipment, to thousands of watts when you add up all the electricity-consuming devices in your home or studio. These four fundamental measurement units are related. The basic formulas that define that relationship is called Ohm's law. It applies to every circuit. It is a simple formula, and you could look it up if you are interested. To use Ohm's law, all you need is very basic algebra. So how does all this background information apply to our job as a recording engineer? Well, like I said, you don't have to understand this stuff to be able to use the equipment. But here are a few takeaways that might give you some useful insights. Now you know that all electricity coming into your studio is ultimately converted to heat. You can see why your control room gets so hot. You can calculate the amount of heat your equipment will generate by looking at the wattage specification for a piece of equipment. Those watts from each unit can be added up and converted to the units used to define the amount of cooling necessary to maintain a certain room temperature. That will help determine the size of an air conditioning system, for example. And you now know that unwanted resistance in the form of oxidized connections can degrade the performance of a connector. You now have a sense of the magnitude of various voltages, currents, and wattages we might encounter, and why that information is important for safety and efficiency. In the next episode of this series on basic electronics, I will talk about additional units and how equipment designers use these principles and others to design equipment that we use every day. And understanding some of the principles may help you to use the equipment better, and that knowledge can be invaluable when something goes wrong. Thanks for listening, commenting, and subscribing. I know this episode departs from my usual discussion of practical matters in the studio. Let me know if you find this valuable. I will intersperse other topics in between some episodes in this series. You can reach me at dwfern@dwfern.com. This is my take on music recording. I'm Doug Fern. See you next time.